For my heat transfer project, I looked into the thermal conductivity of carbon fiber. One interesting fact about carbon fiber is it's anisotropic, meaning at different angles at which the heat is applied, the carbon fiber reacts differently. For example, if that black line on the screen was a single piece of carbon fiber, if we were to apply heat perpendicular to it, it's a great insulator, versus parallel, it would be a great conductor. Also, what affects the thermal conductivity of carbon fiber is the coating, because you can't buy carbon fiber with no coating on it, or else it wouldn't wet out or bind to the resin system. One example of a coating is a diamond vapor deposition, in which you vaporize a diamond and deposit it on there, and that increases the thermal conductivity of the carbon fiber. These are some thermal conductivities published by Dr. Strong, a professor at BYU Provo. Now, the ones we want to pay attention to are the aluminum and the carbon. Aluminum here is under 200, and our carbon, the ultra high modulus, is what we're looking at, is a little under 400. Now compare that to our heat transfer textbook, where aluminum is about the same at 237, but the carbon is at 2000 is much greater than just the 400 we saw from Dr. Strong. So this kind of makes me wonder, what really is the thermal conductivity of carbon fiber, and is it really this great of a conductor? How the experiment was set up is we had a foam block with two hollow cores in it, one for our T hot and one for our T cold. We have a power supply providing our Q, our heat flux, into the system, and we have 5 thermocouples for our T hot and our other 4 thermocouples making a temperature gradient for us. We stuck the whole system inside a vacuum so that we can have virtually no convection and no radiation happening. Now, some assumptions we're making here is that when the power supply is connected, that we're heating up that whole area. Now remember that carbon fiber is an insulator when it's heated from the side, but we're saying that the whole area is heated, and that some of that heat is going to enter from the exposed fiber ends and transfer through the system. You get to see what it looks like in real life. You see our coil on the right and a pultruded rod. Now what makes a pultruded rod very interesting to us is that when it was manufactured, there was a bundle of carbon fibers pulled through a die, and the matrix was applied to it. In this case, it was polyvinyl, and it was cured while the rod was still in tension. Now that gives it some great mechanical properties, but for our purposes, all the fibers are in the same direction, which makes it interesting to us. The data from our experiment. On the bottom right hand, we have the values on the right hand side from Dr. Strong's book, and the middle there is from our heat transfer book. We're going to look at the aluminum wire. Notice that the thermal conductivity, the yellow or orange looking line, is not linear or straight. But from reading chapter 2 of our heat transfer textbook, it explains that in real life, most things aren't linear. They have a parabolic or so as we work our way through the material. And we see about the 1.5 inch mark that really does line up strongly with that 180 mark, which is Dr. Strong lists for aluminum. We move over to the pultruded rod. We're expecting it to have a 11.1 thermal conductivity, and we don't see that at least the closest we see it is at the 1.5 mark. That's the half inch mark, and further out it gets thermal conductivity is better than that, which is interesting. And finally, our dry carbon fiber. Now, interesting about dry carbon fiber, they come in what they call tows. In our case, it's a 3,000 count of individual carbon fibers, all bound together. And the average diameter of a carbon fiber is in between 5 microns and 10 microns. And in inches, that's between 4 to 10 thousandths of an inch. And we just don't have the capabilities to measure that accurately here at the school. So our thermal conductivity could be anywhere between the orange and the red line. And that lines up really strongly with the heat transfer textbook, the 950. Now, we could have a little bit of inflation because when we did the experiment, we didn't have a perfect vacuum. We had only 25 inches of mercury instead of 30 inches of mercury. We could have our seal between the two compartments could not have been perfect, and we could have had a little airflow and radiation, exaggerating what was happening inside there. But we still feel that this is strong. At showing that carbon fiber is an excellent conductor of heat along the axis of the fibers.